lecture. So welcome back everyone. So tonight we are going to continue our discussion on Newtonian astronomy and look at Isaac Newton orbital motion. Do you guys have any questions about last night's work that we covered? This is chapter 4 and 5 of the textbook. So before I'm continuing with this lecture, I want to open up the floor to you guys. Do you guys have any questions, something interesting you want to share with the class, something you have heard or read up in the last week? Yes, I saw the SpaceX debris in the US. I also shared that on my Facebook page. So that was spectacular, but also a mistake from SpaceX. So usually what they do, the first stage they reuse and land again. So the second stage they usually burn up in the atmosphere over the ocean to make sure that nothing bad happens. But this time something went wrong when the second stage was returning to Earth. So they had to burn it out, unfortunately, over a suburban area. So that is scary but beautiful pictures at the same time. So a question, what is parallax again? Okay, so let me go back a few slides and show you parallax. We're going to discuss parallax further in this lecture tonight, but let me go back to I think it's one of the early slides. So yeah, this is parallax. So the best way to explain parallax is, if you look at an object that is far away, that you can cover it with your thumb. So you stretch out in this example, your left arm, you cover it with your thumb and you close your right eye and you look at the object. Then you close your left eye and look at the right eye and look at an object and you see it moved a little bit. And that angle that differs from your left eye to your right eye is called the parallax angle. It's a pleasure. So a few more comments. This may not be particularly interesting, but I found out that the Perseverance rover runs on the same chip that powers Max from the 1990s. That is very interesting, and it also shows how technology has evolved since then. So apparently Mars is leaking water into space. How's this possible? So I haven't read anything up about that. So if you can send me a link, I'll also Google it after class. I haven't read anything about it, but that sounds interesting. So I just want to get to the correct slide again. Oh, thank you for sharing these links. I will read up about that. So I've also found out next week we are following a normal timetable. So you won't have any test clashes on Thursday night. We will still continue with our normal lectures on Monday and Tuesday. So when will Ingenuity fly? So I'm not quite sure, but that will be happen quite soon. I know they have set out a flight path. I know they also named the flight path after Japie van Zyl. That was the Namibian-born engineer that studied at Stellenbosch University, and he became the director of solar system exploration at NASA. In the last 10 years, I had a little bit of contact with him. Unfortunately, he passed away and wasn't able to see his pet project, the rover and Ingenuity, continue on Mars. Okay, so Monday's public holiday, so we'll only have class. Thank you for reminding me on Monday's a public holiday. I don't keep track of public holidays anymore. But thank you for letting me know, so you only have class on Tuesday. So from this image, you guys that are fans of Neil deGrasse Tyson will probably remember him saying this is his man, and he's a big fan of Sir Isaac Newton. Mr. Groenewald, what do you mean you love that story? Which story? Ah, okay, awesome. So let's continue our discussion on Isaac Newton and his influence in astronomy that we now know today as Newtonian astronomy. So if any one of you have any say ideas or suggestions that what Isaac Newton contributed to astronomy. So Mr. Louis, greatest scientist to have ever walked this earth. I will agree with that statement. So yes, calculus is an important piece of tools we need to do astronomy. Basic understanding of gravity, exactly. Gravity is important. Optics is important. So have you ever thought about Isaac Newton, what he did during his life? So he invented calculus before the age of 27. That is astonishing. So Isaac Newton and orbital motion. The problem of the space place of Earth was resolved by the Copernican revolution, but the problem of planetary motion was only partly solved by Kepler's laws. For the last 10 years of his life, Galileo studied the nature of motion, especially the accelerated motion of falling bodies. Although he made some important progress, he was not able to relate his discoveries about motion on Earth to that of the heavens. That final step fell to Isaac Newton. He made most of his discoveries in optics, mechanics, and mathematics. Among other things, he studied optics, developed three laws of motion, defined the nature of gravity, and invented calculus. The publication of his work, in his book Principia 1687, placed science on a firm analytical base. So something interesting, his book Principia can be downloaded. You can have found a ebook of it. I know the first edition of this book is somewhere in a museum. I'm not correctly sure which one. So before Katiana, you guys still remember Newton's three laws? Awesome. So this is the first edition of Sir Isaac Newton's book. This is considered as the holy grail of science, because this is actually a first book that describes gravity, his laws, calculus, optics. So this is where the holy grail of science started. So here we can see one of his pages on orbital motion. A bit of his other notes on orbital motion. So when we look at a timeline on where all the great scientists and philosophers lived, we have in the 1500s, we had Copernicus, Luther, Michelangelo, Leonardo da Vinci, Columbus. Then from 1543 to 1642 is 99 years of astronomy. So here we had Galileo, Tycho Brahe, Kepler, Shakespeare, Elizabeth I, Guy Fawkes, Rembrandt. So in 1666, that's where the Black Plague began. So we have here the 99 years between the death of Copernicus in 1543 and the birth of Newton in 1642, marked the transition from the ancient astronomy of Aristotle and Ptolemy to the revolutionary hypothesis of Copernicus, and simultaneously the invention of science as a way to understand nature. So now Beethoven wasn't an astronomer. This is just to show a timeline where prominent figures in history lived, was born and died, to show just a bit of a timeline where astronomy fit in. Newton extracted three laws that relate the motion of body to the forces acting on it. These laws made it possible to predict exactly how a body would move if forces were known. So Newton's three laws, just a summary. Law 1, a body continues at rest or in uniform motion in a straight line unless acted upon by some force. Newton's second law, the change of motion of a body of mass is proportional to the force acting on it and is in the direction of the force. Then the third law, when one body exerts a force on a second body, the second body exerts an equal and opposite force back on the first body. So, apparently Newton developed calculus, optics, and theory of gravity during the plague. Yes, he did it during the plague. So, for those guys that listen to Star Talk, I listen to Star Talk of Neil deGrasse Tyson weekly. He discussed this over December, that there was a plague and they also had some sort of isolation, and during that isolation, that is what he came up with. So from this slide, where do you guys guess we are going next? Yes, we are building up to the universal law of gravity. So just a recap on Newton's first laws. So if an object is at rest, it will stay at rest unless a net force acts on it. And if an object is in motion, it will stay in motion unless a net force acts on it. The second law, the more force, the more acceleration, the sweet and the short. Then the last law is every action has an opposite equal reaction. So are you guys all happy with the three laws, or do you guys need an explanation? Want me to go through them again, or are you guys happy? Okay. So then, who can tell me about Newton's law of universal gravitation? Any volunteers? Yes, Mr. Fisagi.
If I remember it correctly, is the distance, or it's the gravitational constant, with the product of the two spheres at their centers, divided by their distance squared. So essentially,
Yes, that's exactly it. In reading the comments, two objects of masses exert a force that's inversely proportional to the center squared. That's precisely it, on the spot. So, the law of universal gravitation states that every point mass attracts every other point mass in the universe by a force pointing in a straight line between the centers of mass of both points. And this force is proportional to the masses of the objects inversely proportional to their separation. So here we have force 1 equals the same as force 2. So here we have the gravitational constant, mass of the 1 times mass of the 2 over r squared. So I know this is a bit nerdy, but you can use this law as a pickup line. You can tell someone, well, according to Newton's universal law of gravitation, one body will attract another body. So that's just something cheesy, and I've been waiting a long time to make that joke. So has this worked on you, sir? Unfortunately not. My girlfriend usually laughs if I tell her this joke. So yes, it's a literal theory of attraction. Yes, Mr. Vandenberg. So see a few comments. So each body in the universe attracts every other body with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distances between the centers. Yes. Uh, you can try again, or otherwise you can type as well. So while we are on this slide, let's do a little mind exercise. So if we look at our, can everyone see the pointer on the screen? Okay, so if we have our mass 1 and our mass 2, what would happen to the force if we increased both of the masses? Yes, the force will increase. So what will happen if we only increase one of the masses? Yes. So now if we look at the distance between them, the r squared, what will happen if we increase the distance? Yes, so exactly, decrease. So you're right, from a mathematical point of view, you're divided by bigger numbers. So in that reasoning, if we make the distance smaller, what will happen then? Yes, that will completely increase. So something interesting you will note throughout your careers, especially when making mathematical models about certain phenomena, it's easier to use point masses. Have you guys any idea why I say that? Any suggestions? Yes, you can go ahead.
So is it not because the force of gravity acts on all the particles of the object, so just representing it as one point mass would simplify the problem?
Yes, that's exactly it. So if you think about the maths, so if you have everything as a point mass, then that is easier to use. So say for example, we are using the same formula and we want to, for example, do the attraction, for example, between a chair and a table. How do you model a chair and a table in this equation? So by using a point mass, it makes it a little bit easier to do the math. And yes, Mr. Groen was correct, mass may not be distributed evenly throughout an object. So when we usually in these models, we start out with point masses. Then after point masses, we use spheres. Have you guys thought about that? So just hang on a minute. I just want to get a book. I want to share something with you guys. So I'm just reading a quote here. Just trying to find a quote now. Yes, I found it. So I'm just going to put on my camera quickly. Can you all see me? So I'm just quickly going to hold this up to camera. So this is a book, if you have free time, I strongly recommend reading. It's Astrophysics for People in a Hurry by Neil deGrasse Tyson. Uh, as you probably realized, I'm a big Neil deGrasse Tyson fan. So in this book, he's speaking about spheres and point masses. So here's just a little bit of a joke I want to share with you guys that he has written. So I am reminded of the half serious joke about how to increase milk production on a farm. An expert in animal husbandry might say, consider the role of the cow's diet. The engineer might say, consider the design of the milking machines. But an astrophysicist who says, consider a spherical cow. So by making use of mathematical models, things just becomes easier making use of point charges and then spheres. And then from spheres, you can use more complicated forms if needed, but usually you will get by making use of a point charge. And now we're starting to get to interesting part of astronomy and also a bit of an interesting part of physics, and that is orbital motion. So Newton's laws of motion and gravitation make it possible to understand why the moon orbits the Earth and how the planets move along their orbits around the sun. You can even discover why Kepler's laws work. To understand how an object can orbit another object, it helps to describe orbital motion as Newton did, as form of falling. So going back to the previous formula, have you ever thought about a great example? So you have all realized the moon's effect on Earth is tides, right? Have you guys ever heard of Earth tides? So Earth tides, I'm going to type it as well. So the easiest way to see the gravitational effect from the moon on the Earth is by tides, right? You have low tide and high tide. But we also get tides on land. We call it earth tides. So we have done measurements at Hadrau. Because Hadrau is not in a residential area and it's basically in the middle of nowhere, the ground literally lifts up by 25 to 27 centimeters when it's high tide, and the ground literally pushes down by 25 to 27 centimeters when it's low tide. We did the same observations in the CBD of Johannesburg and in the CBD of Pretoria, and as well as residential areas, because there are a lot of foundations in residential areas and in city centers itself. So the earth tides in residential areas and in city centers is usually between 3 and 7 centimeters. So I don't think you guys ever realized that or thought about that? So at the ocean, you can visualize it at the ocean because the ocean, we have a liquid form that is not bound as tightly as splits. So we can see the effect of tides easy at the ocean, but we get the same effect on solid ground as well. So if you think about it, if you are in the middle of nowhere, no residential area around you, the ground is literally lifting up by 25 to 27 centimeters when it's high tide and gets pushed down by 25 to 27 centimeters when it's low tide. At your home where you are sitting, that can be between 3 and 7 centimeters. That's a daily occurrence. So there's a few ways you can. Does this affect buildings? So let me try and answer. Okay, so let me answer all three of these questions. So the first one is, does it affect buildings? Yes, it does affect building. That's why the buildings have different sections so that a building can expand and subtract. So usually when you build buildings, you need to account heat as well. Usually metal in buildings um, shrink when it gets colder, gets longer when it gets warmer, so you have to account for that. And then they also have to account for the tides as well. You don't have tension in breaking something. So when you design a building and build a building, that has to be accounted for. And why is it less in residential areas? It's less in residential areas due to foundations. You build a foundation on building to get your building as stable as possible so you don't have any earth move. So you just think about it. You can't build a building just on top of ground because tides and movement of the ground will cause damage to your building, even cause your building to collapse. So in residential areas, you build foundations, and the main purpose of foundations is to keep the building as stable as possible. So that is why the movement is smaller in residential areas. So what is actually moves is the ground. Is it just like a surface, or is it deeper? So it's surface movement of um, that's actually moving. And then how do one actually measure that? So let me quickly see if I have a picture available. Uh, no, I don't have a image available. Um, I should have an image somewhere. Let me see if I can. I should have an image somewhere around here. Uh, so if that all fails, let's use Google Earth. Then I can properly explain how we made these measurements and how we do these measurements. If Google Earth is going to open, okay, let me get a satellite view of this. I'm going to share my screen. Okay, can everyone see the screen I'm sharing? Okay, so this is the Hatrail site. So I'm going to try and zoom in as much as possible. So as this is working, can you all see my mouse cursor? Okay, so what we do is, this right here is a device. It's manufactured by Leica. So all of you are probably familiar driving or driving past a construction site, and you will see one guy that looks through something that almost looks like a camera, and then a bit further away there will be someone with a meter stick. Have you guys seen that before? Basically, they use that in civil engineering to level out the ground and to determine if something is level. So it's basically the same principle. So the device we have from Leica does almost the same thing, but it shoots a little laser. So everywhere on a site, like over here, we have that white pillar. We have another white pillar here, another white pillar here. We have a few buildings here, another building here, another white pillar, another white pillar. And on those pillars, we have prisms. And we, by shooting from the Leica site, a laser to that prism, we can calculate the exact position of that prism to an accuracy of 3 millimeters. So by doing that a couple of 100 times per day, we can see how it's moving, and by that we can determine where the high tide, low tide effect. And we also use that to determine the heat effect. So for structures shrinking, structures putting out due to heat. So we need to use that information to calibrate our telescopes. So to give you an overview of the site, this right here is the original 26-meter telescopes. It's 26 meters in diameter and about 10 stories high. Then over here is our 15-meter telescope. That was the prototype for the CAT-7 telescope. In this corner right here is the HIRAX telescope. That's the prototype of HIRAX being constructed at MeerKAT. That's a project of the University of KwaZulu-Natal. So HIRAX just looks at the sky, and the telescope array is not moving. They are using the Earth's moon to point it to different objects. And then over here we have our newly built VIGOS telescope that is 13.5 meters in diameter. We are still commissioning this telescope, and that will be formed part of the VIGOS VLBI network. So VLBI stands for Very Long Base Interferometry. So that is when a lot of telescopes around the world look at the exact same object at the exact same time, and by doing that you can construct a large virtual telescope that is as big as the distance between the individual telescopes looking at the object. So in this building right here, we have a satellite laser ranger that will determine the orbit of satellites with. Here we have our lunar laser ranger that will determine the orbit and position of the moon, and in here another satellite laser ranger. So you know how expensive it is to construct a telescope. So telescopes on this scale is extremely expensive to build. VIGOS telescope right over here that was built from 2017 to last year. It was at a cost of 56 million rands, if I'm not mistaken. And if I'm not mistaken, for this entire observatory, I think if I'm correct, our operational costs is 40 million rand a year, and that excludes research costs. But thinking about it, with all the money that's available through government programs, that's a really, really, really small piece of the pie. So, question: how do observatories make money? So, observatories is not built to make money. Observatories needs to be funded, and we do research from the observatory. Sometimes you can develop new technology, you can get patents on it, and you can make a bit of money from there. You can do public visits, make a little bit of money, but the main idea of observatories is to do research. So thinking about all the money going around in government, what everything is used to. Have you guys ever thought about what it cost um, for Port Elizabeth to be changed to Gqeberha? Yes, that costs money and millions of rand. I'm not completely sure, but the last figure I've saw it cost something like 16 million rand to change the name. So if you ever think about it, King Goodwill that passed away a couple of weeks ago, that happened during the peak of load shedding. So Eskom decided they are going to run diesel generators. So King Goodwill's uh, what's it called? The ceremony and everything around that, and the entire funeral can be aired. While load shedding is on, Eskom made use of diesel generators to account for it. So just by using that diesel generators to get a surplus of energy for 4 hours in the network costs 20 million rand. So if you think about that, that is costs, just money just thrown at stupid things. So 14 million rand a year to run an observatory, that's not bad if you think about it. Yes, exactly. So I can't remember the exact detail. Last year when they had the COVID relief fund that everybody could use, I can't remember, was that 500 million or 500 billion rand? Is one of the two. So that was used for COVID relief. So is 500 billion. So thinking about 500 billion going to 40 million, how small of a piece of the pie is that? That's not even 5%. So if you think about it, if you go, so let me show you this site. Now we're a bit off topic, but this is really interesting. I'm going to show you this topic. Greenbank, West Virginia, where I spent a lot of time as well. I'm going to go to Greenbank. This is the world's third largest telescope. This is the observatory. So this is the Greenbank telescope. It's the world's third largest telescope. It's 110 meters in diameter, and that is 50 stories in the sky, so higher than the Dalton Center in Johannesburg. So I did go there for research. I spent a lot of time there as visiting researcher. So this year they have 12 telescopes on their grounds. So you can see here's one, over here on this path is 3 more, here's another one, another one, another one, another one, another one. There we can see one, here we can see one. So they have 11 telescopes on site. To run their observatory costs $200 million per year. So to run the Green Bank telescope, the world's third largest telescope, to run it costs more or less $2.50 per second, so more or less $200 million per year. So if you think about the US military budget, right now currently that is $740 billion per year. So thinking about to run the third largest telescope in the world, that's only a piece of the pie, a small piece of the pie. Looking at the entire US GDP, the research programs, the funding going to research programs is less than 10% of the entire GDP of the country. NASA only receives 0.5% of the GDP. So the rest of the other money usually goes to, currently 60% of the US economy goes to the military. So another question, what's the world's largest telescope? The largest telescope in the world currently is FAST, that's in China. That is 500 meters in diameter. Not $400 billion to the army, $740 billion. The world's second largest telescope is the Arecibo Observatory that unfortunately collapsed in December due to damage from tropical storms. Then the third largest telescope is the Green Bank telescope. When the SKA is going to be operational in 2030, then that will become the world's largest telescope. What year was, what do you mean, what year was this? So the SKA will be operational in the year 2030. So unfortunately, research is a little, so exactly like I said, minuscule in comparison to other budgets. So everybody thinks to do research costs lots of money. Yes, it costs lots of money, but thinking about other programs, such as the military programs, that gets lots and lots of money, more than the research programs we have. So does HeartRail do visits? Yes, HeartRail does visits. So let's go back to HeartRail on this. So HeartRail does public visits. Unfortunately, with COVID rules and regulations, we do not take visits currently. There's also public visits at Meerkat. Unfortunately, there's no public visits there due to COVID. So I planned a field trip for the class to go to HeartRail, but unfortunately, with the current COVID regulations, we are not allowed to go. but I will see if there's a chance the university and ARTRA will agree to a visit, and I will let you guys know. So with the SKA being built, yes, astronomy is now a very hot topic in South Africa, and if you want to get into astronomy, now is the ideal time. There's a lot of astronomy bursaries going around, especially through SARAL. I'm going to type it in, so I'm going to end this. I'm going to share the correct slide, and I'm going to type it now in chat. Let me get to the correct slide. Orbital motion. So for radio astronomy, our governing body is SARAL. It stands for the South African Radio Astronomy Observatory. They have a lot of bursaries and funding opportunities. For optical astronomy, we have the SAAO, the South African Astronomy Observatory. So there are talks from the Department of Science and Innovation in government to merge these two organizations. So depending on if you want to go optical or radio, then those two are the correct organizations to follow. So yes, these two, SARAL and the SAAO, provides internships as well. That's how I started my career. So when I finished my undergrad, I did an internship at Hadra. So let's continue on with the slides. So an object orbiting Earth is actually, so question, what was my undergrad in? So I'm one of the weird and crazy people that did two undergrad degrees at the same time. I did a Bachelor of Science in Computer Science and a Bachelor of Science in Electrical and Electronic Engineering at the same time for my undergraduate, and then I did a master's in radio astronomy. So you say how? So I did my undergrad at the University of Johannesburg. Uh, at the University of Johannesburg, they have a double degree program where you can actually take Bachelor of Science in Computer Science and Bachelor of Engineering Science in Electrical Electronic Engineering at the same time. So for my undergraduate degree, I didn't really have a social life. I studied my ass off, but it all was worth it at the end. And that's something for you guys also to think about. So astronomy is a postgraduate qualification. So if you want to end up in astronomy, there's a few routes you can take to get to astronomy. So you can either do a general BSc, you can do a BSc in physics, BSc in math, BSc in applied math, BSc in computer science, you can do engineering, electrical and electronic engineering, and then from there you can do and specialize into astronomy. So are there astrochemistry? Yes, there's astrochemistry. That's a field that is becoming quite important in today's time. There are also astrobiology, there's astrophysics, there's astrogeology, there's astroengineering. So it all depends on what you want to do with your career. So I don't want to discourage anyone, but if you want to work in the field of science and especially in the field of astronomy, unfortunately you need a master's as minimum qualification, preferably a PhD, especially in academia as well. If you go to industry, it depends on what you want to do in industry. Industry is a normal bachelor's, will open all the doors necessary for a successful career in industry. If you have a honors, that will be better for industry, but if you want to be in a research career or in academia, then unfortunately you will need a master's as minimum and PhD preferably. So that can be a long road ahead, but it will be worthwhile. So continue with the slide. So an object orbiting Earth is actually falling, so being accelerated towards Earth's center. The object continuously misses Earth because of its orbital velocity. To follow a circular object, the object must move with circular velocity. And at the right distance from Earth, it would be a very useful geosynchronous satellite. So are you guys comfortable with the term of falling and missing Earth? Okay, so let's draw. I'm going to draw on this slide, so hopefully this will help a little bit. So if we are moving, so first before I draw, we can see here is our different orbits. So it doesn't matter where we are around Earth, we are being pulled with the same amount of force. Let me get a better color. So it doesn't matter where we are pulled to the center of Earth. Doesn't matter where we are. So when we are in orbit, such as this object right here, we are being pulled to the center of Earth. So when we speak about an orbit, we use our orbital velocity. Another word for this is circular velocity. So let's imagine we have a cannon over here, and we have a circular velocity that is less than our acceleration towards Earth, then we will be pulled to Earth. If the velocity is a little bit more, we will still be pulled towards Earth. If our velocity is greater than the gravitational acceleration to Earth, then we will move on this orbit. So we are still being pulled inside, but we can imagine it as falling besides Earth, missing Earth, but the gravitation still pulls us closer, and that creates an orbit around Earth. If the velocity is faster, then we will have a higher orbit. If the velocity is faster, then we have even a higher orbit. So this is a branch of physics and math called orbital mechanics. So if you think about it, if we are in a spaceship orbiting Earth, and we want to get to an higher altitude, meaning an higher orbit. What do you guys think we need to do to achieve it? So does this relate to the slingshot? Yes, it does relate to the slingshot concept as well. Yes, that's exactly, it's spot on. We need to increase our velocity. So if you want to get in a higher orbit, we need to increase our velocity. So what will happen if we want to get into a lower orbit? Yes, we have to decrease our velocity. That's exactly it. So it's counterintuitive thinking about, so if you're in a spacecraft around Earth in orbit, if you want to be in a higher velocity, you can't just pull your joystick backwards and say now we're going up, or push it down and say now we're going down. That will do absolutely nothing in space. So to get higher, you need to increase our velocity, and to be in a low orbit, decrease our velocity. So when you look at the International Space Station, the International Space Station is roughly in orbit 400 kilometers above Earth's surface. But to keep it in a stable orbit at the same altitude, every now and again they have to fire up thrusters to increase the station's velocity to keep it in a stable orbit so it misses Earth and free falls basically around Earth. So when we speak about geosynchronous satellites, that's an orbit that is far away, that is it's in with sync with Earth's rotation. So how do they refuel? That's why there are resupply missions to the International Space Station. Yes, people are saying so. Usually, when you see there's a resupply mission to the International Space Station, that is usually for supplies for the astronauts, tools, and also fuel for the thrusters to push the space station in the correct orbit. Okay, so you guys now are happy with orbital motion and being accelerated and continuously misses Earth, these concepts. Awesome. So here is exactly what I explained, but just with a different image. We have a cannon launching it. So if our orbital velocity is slow, we will crash back into Earth, but if we get it to a certain speed, we can be in orbit. So how many of you guys have watched SpaceX's launches? Thanks for sharing. So looking at SpaceX launches, so usually in my slides, I would have now shown you the launch of the Falcon Heavy, the first flight of Falcon Heavy, but unfortunately I can't show that through Blackboard Collaborate, so I will post to you a link to the video. What is something of the speed of the second stage that you guys notice every time? So they tried to get the speed up to 27,000 kilometers per hour. 27,000 kilometers per hour is escape velocity of Earth. If you're traveling faster than 27,000 kilometers per hour, then you can escape Earth's gravitational pull. So to end up in this path, I don't know, the speed you need to end up with is determined of where you want to be in orbit around Earth. So we can call it LEO. LEO stands for low Earth orbit, or it can be in high Earth orbit or geosynchronous orbit. So depending on where in orbit you want to be, you need to get the exact speed. So usually to get to the exact place you want to be, you accelerate to 27,000 kilometers per hour. That is escape velocity. And when you reach or close to the position in orbit you want to be, you start de-accelerating to get into a stable orbit. Are you guys comfortable and familiar with a geostationary orbit? Okay, for those saying no, have you guys ever thought the DSTV dish next to your houses? It points to a satellite, but that satellite needs to orbit Earth. But so if it orbits Earth, that means our dish needs to be following that satellite, but that satellite is on the exact same place. And that satellite being at exact same place is called a geosynchronous orbit. So if I draw on this screen, if this is Earth and Earth is rotating and we have a satellite over here, the speed at which the satellite orbits the Earth is the exact same speed as the rotation of the Earth. And that causes for our perception that a satellite remains at the exact same place in the sky, and we call that a geosynchronous orbit, and that is at 36,000 kilometers above Earth's surface. Everybody happy? So how do they control the speed that satellites orbit Earth? So all satellites have thrusters on board, or some sort of propulsion. Is usually thrusters. So to keep the speed constant, every now and then you have to fire up thrusters to get this velocity correct to remain in that orbit. So usually when a satellite is at its end of its lifetime, they usually deorbit it, meaning they increase the velocity and push it out into deep space, or they decrease the velocity and let a satellite burn out in the atmosphere. So has there been any objects that hit satellites? Yes, that happened. That has happened before. So with there's so many satellites in space, you can think of space in orbit around Earth. You can think about it as a full parking lot with cars. So to launch a satellite now these days, you have to get your window of launch just right, so you can get your satellite to the correct space. It needs to be in orbit without hitting anything else. So another question is, how do they calculate the speed of the Earth? We can calculate that by doing observations. Remember, everything is in reference frame, and then when you go to Newtonian classical mechanics, you can calculate the rotation by making use of Earth's gravity. So that's something you'll do in your physics courses by making use of a pendulum, and then you can know what a gravitational pull to the center of Earth is. We know that is 9.8 Gs. And from there are formulas that you can calculate the rotation speed of Earth. It's a pleasure. So now, notice that objects orbiting each other actually revolve around the center of mass. So thinking about these two objects, we have the Earth and we have the Moon. So they are different masses, but between them there will be a common point where both objects will revolve around. So in the instance of Earth and the Moon, that point where both revolve around is below the surface of the Earth, and that gives us the impression that the Moon is orbiting Earth. So from this image we can see, to be accurate, you should not say that an object orbits Earth, rather than the two objects orbit each other. Gravitation is mutual, and if Earth pulls the Moon pulls on Earth. The two bodies revolve around their common center of mass, the balance point of the system. So are you all comfortable with this idea? So two bodies of different mass balance their center of mass, which is located closer to the more massive object. As two objects orbit each other, they revolve around their common center of mass, as shown in the figure. The center of mass of Earth-Moon system lies only 4,670 kilometers from the center of Earth, inside Earth. As the Moon orbits the center of mass on one side, Earth swings around the center of mass on the opposite side. And then finally, notice the difference between closed orbits and open orbits. If you want to leave Earth to never return, you must give your spaceship at least escape velocity. So that is an open orbit. If you are remaining around an object, then you will have a closed orbit. So looking at our solar system, everything is in the same plane except Neptune and Pluto, that has eccentric orbits. So close orbits are repeating cycles. The Moon and artificial satellites orbit Earth in close orbits. Below, the cannonball could follow an elliptical or a circular closed orbit. If the cannonball travels at velocity needed to leave Earth permanently, called escape velocity, it will enter an open orbit. An open orbit does not return the cannonball to Earth, it will escape it. So here we can see different orbits. So as described by Kepler's second law, an object in an elliptical orbit has its lowest velocity when it's furthest from Earth, so at apogee, and the highest velocity when it's closer to Earth, so perigee. So perigee must be above Earth's atmosphere, or friction will rob the satellite of energy and will quickly fall back to Earth. So here we can see a cannonball with velocity greater than escape velocity will follow a hyperbola and escape from Earth. A cannonball with escape velocity will follow a parabola and escape, and in here we have our different orbits. So do you all recognize this starship? Yes, Star Trek. What is the ship's name? It's the Enterprise. So just, yes, it's the Enterprise. So I'm a big Star Trek fan, especially Star Trek and Star Wars. This is my favorite spacecraft of all times. This is the Enterprise D. So let's all imagine we are on the Enterprise and you ask the helmsman to put us in a stable orbit. What is he actually doing? So what is he programming the computer to do with the ship's engines? Yes, so use less thrust, so meaning get the speed or velocity correct, So we can free fall around an object and call that a stable orbit. So that is correct. So now we have a little example that you all should remember and pay attention to. So in a textbook, there's reasoning with numbers that is important. So here we have circular velocity. So circular velocity is the velocity a satellite must have to remain in a circular orbit around a large body. If the mass of the satellite is small compared with the central body, then the circular velocity is given by the equation. So circular velocity equals the root of gm over r. And this formula, m is the mass of the central body in kilograms, r is the radius of the orbit in meters, and g is the gravitational constant. This formula is all you need to calculate how fast an object must travel to stay in circular orbit. So for an example, how fast does the moon travel in its orbit? So the mass of Earth is given here, and the moon orbits at this distance from Earth's center. So you plug that into our equation, and we have a velocity of 1,020 meters per second. So this calculation shows that the moon travels at 1.02 kilometers along its orbit each second. Straightforward. Do you guys have any questions so far? You guys all happy? Okay. So now we get to tides. So Newton understood that gravity is mutual. Earth attracts the moon and the moon attracts Earth, and that means the moon's gravity can explain the ocean tides. But Newton also realized that gravitation is universal, and that means there is more to tides than just Earth's ocean. So here we can see the lunar gravity acting on Earth. So we have the moon here. So here we will have high tide, and we can see the pull over here. So both on both sides of Earth, due to the gravitational pull of the moon, we have tidal bulges. So over here we'll have high tide, and over here we will have low tide. So tides are produced by small differences in gravitational force exerted on different parts of an object. The side of Earth nearest the moon feels a larger force than the side furthest away relative to Earth's center. Small forces are left over and they can cause tides. Both the moon and the sun produce tides on Earth. Sometimes they add together and sometimes they partially cancel. Tides can even alter an object's rotation and orbital motion. Where did I miss a question somewhere? So where do we get the denominator from? That is just a given to us. So something interesting that you guys haven't thought about, I presume, is the Earth, the moon is tidally locked to Earth, meaning these bulges are always at the same place. So with the gravitational pull, while Earth is rotating through these bulges, and that causes tides. but the sun also has an influence on tides. So the sun is roughly 27 million times more massive than the moon, but it lies almost 400 times further from Earth. Consequently, tides on Earth caused by the sun are less than half as high as those caused by the moon. Twice a month, at new moon and at full moon, the moon and sun produce tidal bulges that add together and produce extreme tidal changes. High tide is very high and low tide is very low. Such tides are called spring tides. Here the word spring does not refer to the season of the year, but to rapid welling up of water. At first and third quarter moons, the sun and moon pull at right angles to each other, and the sun tides cancel out some of the moon's tides. These less extreme tides are called neap tides, and they do not rise very high or fall very low. The word neap comes from an obscure Old English word, nept, that means to have, meant lacking power. So just another hint for tests and exams. Everywhere where I highlight words such as these are definitions that you guys should know. So from here we can see we have spring tides when the sun and the moon lines up, then we get high tide, low tide, low tide. So the Newtonian universe. Astronomers built on the discoveries of Newton, just as he had built on the discoveries of Copernicus, Tycho, Kepler, and Galileo. It is the nature of science to build on the discoveries of the past, and Newton was thinking of that when he wrote, "If I have seen further, it is by standing on the shoulders of giants." And you guys know who also said the same quote? Except Tyson. Our other main man, Albert Einstein, he also said, "If I've seen anything, it is by standing on the shoulder of giants." And there's one other person in recent times that also have said the same quote. You guys know who? Yes, Stephen Hawking. And I think Penrose said it too. But on the shoulder of giants, the great works of physics and astronomy from Stephen Hawking. And then, by building on top of each other's work, science can also take a little bit of a dark step. So, when they tested the first atomic bomb, Robert Oppenheimer said, "I am become death, the destroyer of worlds." And that, ladies and gentlemen, is chapter 4 and 5 of the textbook. Do you guys have any questions? So one thing before we end is just something Professor Brian Greene, he is involved with CERN, has said. So the moment civilization will jump to a new level is when young kids look up to scientists the same way they look up to celebrities. So you think about it, 100 years ago, 100 years ago, scientists, 150 years ago, scientists were considered rock stars. Take, for example, Albert Einstein was the last rock star scientist. When he went for a conference from the US to London, he went by ship. So when he arrived at the port of London, if I'm not mistaken, something like 16,000 people were waiting at the port to see him. That's the status he wore and achieved as scientist. But somewhere in the last 100 years, something dramatically wrong somewhere, and people don't look up to scientists, engineers, mathematicians, physicists, astronomers as they used to. And that is something for you guys to think and ponder about. So what would tides look like during a lunar eclipse? So that would be spring tides. So ladies and gentlemen, if you have no further questions, then have a great evening. Good luck with your other modules for the rest of the week. I will see you all in next week's class. Thank you so much. I saw here, where's that comment now? I think it's the availability of the internet. It has made it simpler to find information. That could be one of the contributing factors. Yes, Mr. Visagi.
Professor, just getting back to your thing about why people don't look up to scientists and engineers, it's also probably because science and engineering has become so common around the world.
That can also be why. So there's a few studies actually going on where we try to get more people or young persons involved in science. So one of the projects I'm involved with to get young people and people in general more interested in science is, we call it sidewalk astronomy. So I'm part of a few astronomy clubs. So we would take a bunch of telescopes, we would go to a shopping center or a mall, we would set up our telescopes in the parking lot, and then when people are going by, we would say, hey, have you ever seen Saturn before? Have you seen Jupiter? Have you seen the moon through a telescope? And that is one way we try to get people interested in science.
That does sound interesting, Professor. I was actually wondering, what does it look like through the telescope?
So if you look through different objects to telescopes, that is extremely beautiful to see. So previous years, specifically for this course, there was an astronomy evening organized for the class. I don't know with COVID restrictions if it will happen this semester, but I will find out from the HOD, and perhaps we can organize an astronomy evening for the people that's in the Pretoria area. Awesome. So I'm going to stop the